tenido un impacto tremendo. Se ha ganado, digamos, cada premio que se da en la astronomía, Sandy se lo ha ganado. Si fuera general, estaría cubierta de medallas. Se ganó el premio Gruber de Cosmología, que es un premio muy importante, la medalla de oro de Bruce. Ella es miembro de la Academia de Ciencias de Estados Unidos. Y un reconocimiento muy importante que se ganó fue la medalla al mérito científico que se la dio el presidente Obama. Y bueno, tuvo mucha suerte que se lo haya dado el presidente Obama y no el presidente actual. Y realmente lo único que falta, y estoy esperando ansiosamente, es que pues, me invite a Suecia a que le den el premio Nobel pronto. Entonces, porque claramente su trabajo ha sido increíblemente transformativo en todos los aspectos. Quería terminar un poco con la semblanza de Sandy, no solo que vean el impacto que ella ha tenido en la ciencia, sino el impacto humano. Claro, ella como maestra y como asesora ha sido increíble. Un ejemplo claro está aquí en la mesa, el director Chucho que está aquí a mi lado izquierdo fue su estudiante. Entonces realmente Sandy ha creado una generación de astrónomos muy imponente en el mundo. Es una persona con un corazón increíblemente gigante, de una calidad humana maravillosa. Y les quería platicar que en los últimos 4 años, Sandy ha estado trabajando en un evento que se llama La Noche de las Estrellas en el Observatorio de Lick, donde apoya a la comunidad hispana y hace un evento, digamos, en castellano, donde yo he participado y la he apoyado, para las comunidades hispanas locales de donde vivimos, ¿no? Entonces, su manera de realmente apoyar a la gente necesitada en Estados Unidos y de crear una astronomía que refleja el mundo en el que vivimos ha sido una misión muy fuerte de Sandy y realmente es un orgullo tenerla como colega y como amiga. Muchas gracias.
Who will give her lecture on cosmic knowledge and long-term strategy of the human race.
What can I say? Muchas gracias. You have done me such honor and giving me such pleasure by inviting me here. Let me start by returning a little bit and mentioning, I got maybe 10% of what was just said, so if I repeat, please pardon me. Let me start by saying that the ties between Santa Cruz and myself and this department go way back, starting with Chucho here, Jesus, who I should tell you wrote one of the most important theses that ever came out of our astronomy department that established that elliptical galaxies, many of them are young, actually recently quenched. This overturned an old idea and has really revolutionized our thinking about the evolution of these galaxies. And then Enrico arrived, and you can just see what a wonderful and charismatic character he is. He is really helping us establish a more egalitarian and diverse department. He is so passionate about this. Let me move to the present and mention how wonderful my visits in the last 2 days have been to your department here. This Instituto de Astronomía is a world-class astronomy department. You should be very proud. And I had many meetings, and even at one point, it was so interesting, I was moved to say, you know, really, of all the people in the world, I would rather be discussing astronomy with you guys right now. And I meant that. So I'm having a wonderful time, and I hope I can repay just a little bit here in a lecture that I hope you'll find interesting. I suddenly realized that maybe we should have thought a bit more about the lights. Is it possible to turn some of them down? We don't want to turn them all off. I'll let you worry about that. Do you think that people got that message? Okay, so the first few slides doesn't matter. This is my topic, cosmic knowledge and the future of the human race. The basic premise is that everybody wants to know about their past. We all want to know about our roots. Why? Because we feel instinctively that if we know where we came from, we will understand better where we are going. And I'm just expanding that principle now to talk about Earth, animals, and people, and to speculate now about where our planet and our species is going. Now, I was hoping at some point here to find something in Spanish to bring these concepts home, and a miracle occurred, and we saw this sign. Annie, my husband, actually pointed it out. We were in Santiago, Chile, and there's this sign there. It's on a cafe. It's actually quite famous. There are pictures of it all over the internet now. And of course, in Spanish, it means there's more future than past. And I thought to myself, that's exactly the message I want to get across. The cosmic future is very long. That's what I want to talk about. But then I thought a little bit more, and I began to wonder, as I know you all are wondering. Yes, the sun has a long future. Yes, the earth has a long future. The real question is, do we have a long future? So I think that the makers of this sign on the cafe would have done better to put a question mark after it, and that would have prompted everybody who saw that sign to wonder, and that's what I want to prompt in your minds today. I want you to start thinking, to speculate about where we could go in the future and what we need to do to get there. But first, I want to start by giving you a little tour. What I'm going to be talking about in the beginning of this lecture is astronomical things, and I think it would be really nice to start out here, I need to find my cursor here, with a beautiful film, which is a tour of the nearby universe, made by an astronomer at the University of Hawaii. Here we are on Earth, and we're going to take a voyage now through the galaxy. We're going to fly towards Orion. And as you can see, Orion is dissolving because it's not really a group of stars all in one place. It's just an alignment along the line of sight. There's a big cloud of gas there. We'll hear more about it in a minute. It's called the Orion Nebula, where stars are forming. And right behind it is another very famous astronomical feature, the Horsehead Nebula. These are places where young stars have just been born. You can think of them as stellar nurseries. Here's another one, a very famous one called the Rosette Nebula. It's particularly nice. You can see this collection of very massive, very hot, very bright ionizing stars at the middle of the nebula, lighting up the birth clouds. And now we continue to fly through the galaxy. The stars are not all in the right places. We don't know where stars are to that accuracy. But now we encounter another glowing gas cloud, and this is completely different. This is the Crab Nebula, the remains of a supernova, a dying star that exploded about 1,000 years ago. And now, here's the really brilliant part of this film, I think. We're now flying out of the galaxy. You will have seen that it's a flat plane. We're in it. And very skillfully, the filmmakers have morphed into a real galaxy that we know, NGC 5383. And that's the Magellanic Clouds coming into view, Fornax, another spheroidal galaxy. And now the camera view is going to pan over to the other two big galaxies in what we call our local group. This is a small spiral called M33. All of these galaxies have these catchy names. And now it too is full of star-forming regions. We're going to fly through that. In the corner of the view is the big Andromeda spiral, our big sister in space. And now the view pans out beyond the local group. This is where Brent Tully, the maker of the film, his expertise was essential because he, amongst all astronomers, has mapped where the galaxies are. So he's put them in the best positions as far as we know. I'm getting a little echo here. Okay, and now you will see that they're not distributed uniformly. They're kind of in filaments. We're going to fly down a filament here. And where the filaments intersect, we have big clusters. So right ahead of us there is the Virgo cluster, about 1,000 galaxies. And this film is accurate, except that all the galaxies are 10 times bigger than you would actually see them. They have to be that way in order for us to appreciate them in the movie. Space is not really this crowded. Space is pretty empty. And now we're going to wind up at the center of a giant elliptical, 20 times bigger than our galaxy. And at the center is one of the biggest black holes that we know about, many billions of solar masses. So I think that's probably why the film is stopping at that point. All right, so isn't it amazing? We actually, as astronomers, we now know where all of this came from. When I started my studies as a graduate student, what you've seen here is a complete mystery, was a complete mystery. First of all, we didn't really know it was there like that. A beautiful map had not been made. And we had no idea where galaxies came from or how they made stars. So, in order to understand the origin of all of this, and this is really the origin of you, we need to go all the way back, almost to the Big Bang itself. The early universe, almost smooth, but with matter energy density fluctuations at about a part in 100,000. And look at the time, 10 to the minus 35 seconds after the Big Bang, and a temperature of 10 to the 27 degrees Kelvin. So our modern theories of particle physics tell us that this was a very special temperature where the physics of matter energy was very different, and it drove the universe into exponential, uncontrolled expansion. And it was that expansion that actually built these density fluctuations. If you want to know how, ask me in the question period. But those density fluctuations, which were really born as tiny quantum fluctuations, much smaller, billions, billions, billions of times smaller even than an atom, they are the seeds. They're extra matter energy generated extra gravity that caused the universe to be lumpy today. These are the seeds of galaxies. So we are all children of a quantum fluctuation that made the Milky Way. Isn't that unbelievable? I'm going to die happy knowing that. Really, I think that's one of the most profound insights that any of us could ever have about where basically things come from. Heisenberg never dreamed that he would have explained the existence of galaxies, I'm pretty sure. All right, well, we can now take this picture, which is quite quantitative, take the lumps that it predicts, put it into a computer, and generate galaxy formation. So that's the next film I want to show you. A very beautiful film made by some Japanese some years ago, and the graphics are just wonderful. So the very beginning is abbreviated, but you can see that the distribution of matter there is uneven. And it's kind of filamentary. Remember I mentioned filamentary? That's a characteristic of the lumpiness of our galaxy, of our universe. The blue that you see here is primordial gas, hydrogen and helium, and it streams along the filaments, and galaxies form at the intersection, and sometimes they fall in and merge with one another and crash together. So we've looked way back in time here, billions of years back in time, and you get the feeling that the early phases of galaxy formation are quite chaotic, when the universe was still very lumpy, and the lumps crashed into one another and disturbed one another. So the stars here that have formed in this film are the little white dots. Can you see them? I think you can. And this is supposed to be, by the way, our galaxy, the Milky Way. This is a scenario for our galaxy. And you can see as time goes on, we're getting bigger because we're grabbing smaller things. And every time something falls in, it disturbs the previously existing stars. And their gravity of these lumps creates a halo, a spheroid. So we predict the existence of a dense stellar structure, and then whatever gas is left over falls in to make a disk late. So we predict that galaxies should be two component structures, And that's what this beautiful film is telling us. Okay. So now, let's just ask ourselves, why should we believe any of this? I just told you a fantastic story starting with quantum fluctuations at 10 to the minus 35 seconds. Why does this make sense? Well, the reason is that galaxies actually look like this. We have the right numbers, they have the right masses, they have the right structure. These are beautiful pictures taken with the Hubble telescope. And we can see that sometimes they have these big stellar spheroids and sometimes they're more disky. That depends on how many collisions they've had. We know that they're flattened rotating disks because we can see some of them edge on. And I invite you to look at this one. This is particularly beautiful, edge-on galaxy. Just imagine that we lived in the disk. What would we see? Well, this is what we would see, okay? So this is a beautiful wide-angle photo of the center of our galaxy. And I call attention, because I'm going to come back to it later, it's a big part of our story here as Earth people, those dark clouds. Those are dust clouds. The dust grains were grown in the atmospheres of stars and sent out in supernova explosions and stellar winds to populate the gas between the stars. And they're going to be part of our story a little bit later. Okay, so one reason we believe the story is it matches galaxies as we see them. But we can even do better than that. We can follow the story of galaxy formation by looking back in time. And this is where Hubble comes in with this beautiful picture called the Hubble Deep Field, which is, I think, the most expensive image that human beings have ever taken. About $20 million went into this picture, except there might be other pictures I don't know about. Okay, so now this is a completely ordinary patch of sky. It's about 1/10 the size of the full moon. And it contains mysteries. It contains information, which we can tap by making a movie. So that's my next movie for you, made by the wonderful people at the Hubble Space Telescope. And this picture is like a core drilling of space-time. It's like taking a drilling in a glacier and going back thousands of years below the surface. As you know, it takes a while for light to travel. So when you look at things that are farther away, you're also looking back in time. So astronomers have perfected pretty well how to gauge the distances of these galaxies in this Hubble picture. And the movie makers put that into a movie, and now we just flew back in time, back down the arrow of time. And you will have noticed that the galaxies were big at the beginning and small and featureless at the end, and that records the fact that early they were infants and small, and then they grew and drew in more mass. Okay. So let's think here for a moment. How are you feeling? I think really science is missing its full potential if we don't let it touch our feelings. It's not just what we think, it's what we feel. I think this is how we make decisions. So here's how some people feel when they look at that Hubble Deep Field picture. Okay, so astronomy, finding out you really just don't matter. This is a takeoff on something called the Despair Company, which has a wonderful way of taking pictures and then putting words to them that are exactly what you don't want, okay? So some people look at all of these. There are 10,000 galaxies in that picture. There are 100 billion that we can see over the entire celestial sphere. Some people feel very depressed by this. We're insignificant, we're small. How could we be important? Well, that is not my theme. And so I need to continue telling the rest of the story. And the rest of the story, we've made galaxies now. Galaxies are the birthplace of stars and planets. Stars form from dense clouds of gas, we just flew through this galaxy. This was the M33, and we flew right through that little spot right there, and this is what it looks like in the Hubble telescope, a beautiful star-forming region with a cloud of young stars lighting up their birth clouds. Many of the most beautiful pictures ever taken with Hubble are regions like this. I particularly love this one with this little star and its star cave down there at the bottom of the picture. And fortunately, we have one of these regions right on our doorstep. It's Orion. This is how my talk started. So there's Orion, and that clump below the belt is not mainly stars, it's mainly shining gas. So we're going to zoom in thanks to Hubble with the high spatial resolution of Hubble. Fly further in, yet further in, okay? And so now some things are beginning to appear. Look at the bottom of the picture, you can see a dark circle. Now, this is what we really see at maximum Hubble resolution, and I really love this region because it's showing us two different kinds of objects. It's showing us this big blobby cloud, a glowing gas cloud, and it's also showing us in silhouette something dark with a little bright spot in the middle. Now, the big blobby things, in more detail, they look like this. These are solar systems that are just forming. The gas is still falling in, and some of it is being blown out by nearby bright stars. And then later, see, there's a time sequence here. This is the end result of solar systems, solar nebulae that have collapsed. And what we see here is a central star and a dark, surrounded by a dark disk. Remember the dust clouds? That's the dust grains that are making these disks opaque. And we know that they're rotating disks because one of them, out of about 60 or so, happens to be exactly edge on, with its star in the middle and a rotating cloud called a protosolar nebula, which is a mixture of dust grains and gas. Now, these interstellar dust grains perform miracles for us. They are sticky. A dust grain, by the way, is about the size of a particle in cigarette smoke. And that by itself is not very opaque, but when you put jillions and jillions of them in space and look over a long distance, then you get this silhouette effect. So the particles start by sticking to each other, and then in a way we don't really quite understand, they can grow to kilometers in size. And finally, once they're that big, they draw in gas to make still bigger planets. So really what we're doing in this process is we are making rocks. We are making rocks of planets and rocks of asteroids, and they're all comprised of that cosmic dust. And that's why I love this picture so much. Pictures say so much, taken by a really wonderful photographer who pioneered this Milky Way cosmic photography. And it just sort of sums it up for me. There's dust in the galaxy, the center of the galaxy, far away, and there's rocks in the foreground in our planet, and they're the same thing. Now, we've brought the story farther forward and we're making planets. That's good. Let's think more about planets, and when you think about planets, what's the first thing on your mind? The question is, how rare is Earth? Is Earth common or not? There's a school of thought that says that Earth is very common. And an example of this is a famous equation that was invented by the astronomer Frank Drake called the Drake equation. This was about 50 years ago. And he wrote this equation down: the number of detectable intelligent civilizations in the galaxies, trying to estimate that. And the number starts with the number of suitable stars, and then there are a bunch of factors here. You know, is it the right kind of star? Does it live long enough, et cetera, et cetera. So each one of these factors is less than 1 and reduces the chances. Now, if you count, you will see that there are 6 factors in this equation. There's another school of thought called the rare earth school of thought, and they start with a different equation. This is the rare earth equation, basically the same calculation. Now they're calculating the probability of complex life forms. They start out with the same n star, and here are some factors. And for these people, there are more factors. There are 10 factors here instead of 6. And that matters because if each one of those factors is big, I would say 0.1 is big. But when you put 4 of them together, that's a factor of 10,000. So what I'm trying to say is that we don't know yet quite what is required to make an Earth, but the more factors we put in, the rarer we're going to get. And I just point out one factor here, F sub m, is the probability of having a big moon. Remember that. I'm going to come back to that in just a couple seconds. Well, let's talk about some of these factors because I personally, we do not know, I stress this, but I personally think that Earth is rare, and I want to communicate that to you. Thinking about this starts with the concept of the habitable zone. Here is a star. There are planets at different distances. The habitable zone is defined by the distance at which liquid water can exist on the surface of the planet. Okay, but not all habitable zones are habitable. Consider the star at the top, the A star, bright star. It has a short lifetime, only a few 100 million years or less. And, you know, it's taken 4.5 billion years to evolve life as we know it on Earth, so we've got to have a star that lives longer. Now this star, which is very dim and low mass, lives maybe 100 billion years, but its habitable zone is very close because it's a dim star. And in fact, it is so close that the planets around stars like this are probably tidally locked to the star. What do I mean by that? The moon is tidally locked to the Earth, and that is another way of saying that the same face of the moon always faces towards Earth. That would be the case in these stars. The same side of the planet would always face the star. Can you imagine what would happen to Earth's climate if instead of having a day of 24 hours, we had a day of 365 years? One side of the planet would be always getting the energy of radiation. The other side would always be radiating it to the cold outer space. People do calculations about this. You have winds of many hundreds of kilometers a second, so climate is really sensitive to this kind of thing. Here's another factor in planets. Habitability, size matters. You don't want to be too big because big planets have rocky cores, but they have these giant atmospheres that you can't live on. And you can't be too small either. Mercury and Mars in our solar system are no good. They haven't been able to retain their atmospheres because of sweeping by a solar wind. So we know we need an atmosphere, and we have to be the right size for that. Now, here's another requirement which I bet you've never heard of. This is just coming to our understanding. This is rather new. There's something in our Earth that's really quite special called plate tectonics. The center of the Earth is hot. It's heated by radioactivity. It's radiating heat to outer space, and much of that heat is carried by actual circulation motions in a semi-liquid mantle. Convection, in other words, okay? So as these cells convect, they actually bring pieces of land into the core. And this is what is removing carbon dioxide and recycling it in the center of our core. We now know that this process is Earth's thermostat. The existence of these cells over many years, if the Earth gets out of balance with too much CO2 on some time scale, unfortunately too long to do us much good, 100 million years, that extra CO2 is going to go back into the core. This process also scrapes off material and builds the continents. It creates land. And finally, this convection powers the magnetic dynamo that drives the Earth's magnetic field at the currents in this iron core at the center. And here's an interesting thought. water lubricates the rocks, which makes convection possible. If our rocks were not studded with water molecules, they would be brittle and immovable. So flexible rocks with lots of water in them is a key part of our climate. Let's say a few words about water. Hard to get and hard to keep. We don't know where it comes from. We've got a lot. We've got a lot more water in the rocks than we do in the oceans. And just think about that. Isn't that another interesting coincidence? How come there's exactly the right amount of water on the surface to fill the ocean basins? Consider what Earth would look like if it had only 1% of that. We'd have these gigantic cavernous things with little lakes at the bottom, and our climate again and way of life would be completely different. But if we had 10 times more water on the surface, we wouldn't have any land at all, except for a few mountains sticking up here and there. Another incredible coincidence. Nobody knows the answer to this. Venus lost its water because it was too close to the sun and it got too hot, and Mars lost its water, as I've said, because it was too small. I mentioned the magnetic field. Earth's magnetic field protects us from lethal energetic particles that are constantly emitted by the sun. So, what do I mean? How does that work? Let's minify this, put this at the center of the Earth, extend it a little bit. This is what a magnetosphere looks like. It's a pretty strong magnetosphere, and it's sufficient to deflect all of these energetic particles coming from the sun. It protects our atmosphere, and it protects us from lethal radiation. Okay, well, the last factor I want to mention, I mentioned it briefly before, is rare earth and our potentially crucial moon. Remember, remember that factor F sub m? Where did that come from? It came from this. The main thing that we learned from the Apollo rocks was that the moon's composition is almost the same as the Earth's. That is completely impossible for normal theories of planet formation. Every planet should have a different isotopic signature, and yet the moon and Earth look the same. And so that has given rise to the fact that the moon was actually created by a giant collision, which caused much of both bodies to become molten, threw molten material into a disk. It condensed in the moon, and here are some of the consequences. Okay, it's the existence of the moon around the Earth that keeps the axis of our planet oriented in a constant direction. It gives us lovely moderate seasons, which are a nice forcing function for evolution, but don't get out of equilibrium for us. It also gives us the short day and moderates the day-night temperature variation. So there are many people who think that a moon like this is absolutely essential for a planet like Earth. And the probability from modeling is that a collision that we experience, the probability of that is very low, less than 1,000. So that's one factor there in that equation that's very, very tiny. Well, perhaps the best way to find out whether Earth is really rare is to look at other solar systems. And now we're finding planets like this. This was the first one. The first planets to be discovered were massive and close to their stars because they're easy to see using the Doppler method. And they're bizarre. They're objects that have years at the order of days. Since then, we've discovered many more in different kinds. Here's a summary. Here is the year of a planet in days and the mass in units of the Earth mass. So here is Earth here at 365 days and 1 Earth mass. And this is a summary of all the planets that we've found to date, some via the radial velocity technique, some by the transiting technique, mostly with the Kepler satellite. So you will have noticed something really annoying here. Here is Earth sitting, and there's nothing discovered around here, right? Is that real or is that a selection effect? You're a scientist, so I know you know what that means. It is a selection effect. Here's a line that shows us the limits of current discoverability. And it's very annoying and upsetting that our solar system terrestrial planets are sitting in a region that we have not yet been able to sample. Now, nevertheless, some brave souls are undeterred, and they look at this distribution and they calculate probabilities of discovery, and they try to estimate how many planets are here. And you can read papers that say that there are billions of planets like this in the solar system right here. And that might give you hope, except for the fact that we have 3 such planets and 2 out of 3 are no good. So when you hear reports that there are a lot of Earth-like planets, you have to think again, what do we mean by Earth-like? Is Venus Earth-like? No. So let me summarize my thoughts here about rare Earth. There are a lot of very special features about the Earth that we just take for granted, and maybe our combination is extremely rare. We don't know how many Earth mass planets there are. Probably there are many, but not all of those planets in the habitable zone are going to be habitable. So, I see that I forgot to remove a slide, so let me skip through things here. Okay. So the first lesson from all of this is that Earth might be rare, and it would be hard to replace if we ruined it. Now, I promised that I would talk about the future, and we've learned a lot from astronomy and geology about our cosmic future. We're on a good Earth, we know that. Is it a safe Earth? So what is going to put an end to habitability on Earth, and how soon? Well, the first factor is solar warming, the end of the sun's lifetime. The sun is brightening 7% per billion years. This is going to lead to global warming eventually, yes. And this is going to cause a loss of CO2, and photosynthesis is going to stop. So we won't have agriculture anymore. This happens in about 600 million years, unless, by the way, we could move the Earth farther from the sun. And actually, people talk about that. If you've got an asteroid and put it into an orbit that grazed the Earth and grazed Venus, you could transport angular momentum from Venus to Earth and move Earth out. And believe it or not, this is not stupid. Okay, we could be wiped out by a nearby supernova explosion. We know how frequent they are. A few 100 million years to loss of habitability that way. You've all heard about comet and asteroid impacts. We're making real progress there. It was the impact a big impact that killed the dinosaurs. But we're discovering these objects and learning how to divert them. We need some more technology, but I predict that we will be able to discover these and divert their orbits. No problem. Ice ages. Believe it or not, we don't know why there are ice ages. They seem to be sort of recent, actually. Regardless, though, I'm taking the big picture. There's going to be inconvenience. People are going to have to move around, etc. But it doesn't affect basic Earth habitability. The mammals have done just fine through many Earth ice ages. So now let me end with the real problem. The real problem is volcanoes. And the largest extinction in the history of Earth was caused by volcanoes, a volcanic eruption that lasted for millions of years, 250 million years ago. So this could really cause loss of habitability for higher life, and I think we need to study volcanoes more. But even so, it's at least 100 million years. That's the probability. That's a long time. So now let's think about some lessons from cosmology. While I just gave you one, my private feeling that the Earth is incredibly rare and we should take care of it. Here's another lesson, a bigger one. We got here according to the laws of physics, and we are subject to those laws and must live within them. In other words, there were no miracles in our past, and there will be none in future. We are in charge, and it's amazing, I think, the number of people who don't believe this. So if there is one thing that I could pray gets across from the study of science and the study of astronomy, geology, and so on, it would be this. Here's a second lesson. Earth will provide a livable home for at least 100 million years and maybe longer. In other words, we have been given a precious gift of cosmic time, and are we going to use it or will we squander it? And I'd just like to say one more thing about this. What I've been saying here, we are the first generation of human beings to face this challenge. We're the first generation to have this kind of knowledge together with the power to screw up Earth's future. And this raises profound questions about where do we go from here? Well, here's one thing that we can't do. Economic growth. What do we mean by steady growth? If you read the Wall Street Journal, which you probably don't because they are not known for their eloquence in Spanish, but if you were to read them, you would learn that there is a school of thought which is very prevalent, which says that if the economy is not growing, we're actually falling behind. So growth is a kind of steady state in the thinking of our leaders. What is growth on cosmic time? The nominal figure that people love is 3.5% per year. So let's put a bunch of factors together. The economy doubles in 20 years. In your lifetime, 80 years, it's gone up 2 to the 4th. That's a factor of 16. Do you think that the Earth has another factor of 16 left in it in terms of productivity? I doubt that. And yet, I don't know anybody who is studying this. Economists, they want to study growth. They don't want to study the carrying capacity of the Earth. Well, this is what happens in one lifetime. What happens on cosmic time? Namely, 100 million years. Contemplate that. Here's the answer. So 10 with 1.5 million zeros after it. Clearly impossible. What is sustainable growth on cosmic time? It is much smaller. It's that per year, if you allow another factor of 2. And what's the moral? There should be no net increase in resource use. And here's something that we tend to forget about. Waste has to be completely recycled as well by natural processes. So this is my fourth lesson. The fourth lesson is that if we take a cosmic perspective, the meaning of sustainability is completely different from what we're currently talking about. Now in the US, a few years ago, we had a famous film, maybe you saw it here, and here's a cartoon about it, right? So just for those of you who don't know, the film was Inconvenient Truth. It featured Al Gore, who was telling us about the need to save the environment, and not everybody wanted to listen to that. Most people wanted to listen to a reassuring lie about how the future would just be fine. I think this falls way short. Here's the real truth. Okay? We as a population are coming around to the inconvenient truth. I think we're beginning to see that, but we have not yet really come to terms with cosmic reality on timescales of hundreds of millions of years. So I said a while ago that I thought this whole thing is bringing up new moral issues, and that's the thought I want to close with. Being in this new position of power and knowledge in combination, I think this brings up ethical issues that we have never encountered as a species before. I think our ethical system comes from evolution. It's evolutionary adapted, and therefore we don't have these impulses, and this is a problem. We do not have a core feeling about our obligations to future human generations. We don't have an agreed upon decision as whether or not we have a custodial responsibility, a stewardship for Earth. We don't know if there is intrinsic value in the future activities of humankind. We don't feel that humanity has a destiny. No generation has ever thought on those timescales. And the question I ask here is, we have a moral code. Whether it came from religion or whether or not it's evolution genetics based, can it adjust to deal with these new moral questions which have never been faced before? So I'm glad to tell you that maybe a tiny thing is happening at Santa Cruz where we're starting an Earth Futures Institute. The way we envision it, it's the only institute of its kind in the world. Why is it unique? For two reasons. It is focusing on cosmic time, founded by astronomers. You're not surprised that that's the case. But it also has an ethical component to examine our ethics. What is good? What are our values? What do we want? And so on, especially about the future. So let me close with a picture. One of the most striking pictures ever taken by astronomers. This is Saturn, from behind Saturn looking back at the sun. So this is not a view that we see from Earth. We have to send a spacecraft there that will fly around behind it and look back. Absolutely stunning. So it's a picture of a planet. But it's also a picture of another planet. And if you look hard near the middle, there's a little white dot. That's Earth, as seen from Saturn. So now let me return to my astronomy despair theme again. How does this make you feel? Finding out that you really just don't matter? Or, here's what I would prefer to do. I'd like to leave you with this. Okay, this image. Astronomy, why is it useful? Inspiring us to save the Earth by appreciating our cosmic past and realizing that there's a lot of time ahead in which humanity could do great things. So this is not a despair poster. This is an encouraging poster. I leave you with that. Thank you so much.
Okay, now we're going to have questions. So you can ask the question in Spanish if you don't feel comfortable speaking in English. We can translate it.
Can I start with a question?
Yeah.
Okay. I have a question for you guys. Let's imagine that it's 1,000 years from now. And I tell you, you have to believe this, that Earth is a smoking ruin, that it can no longer support higher order intelligent life, and the people to blame, the reason for this is our generation and a few successive human generations that have caused climate change, regardless, whatever. Disaster happened and we did it. Okay. I would like to take show of hands. You have three choices. One choice is you think this is good. Oh, and by the way, it's irreversible. There's no return from this. You think it's good, you think it's bad. And the third choice is you've never heard of a question like this before and you would prefer not to answer for whatever reason, okay? So don't feel bad about that. First of all, who thinks this is good? Raise your hands. It's the first time that nobody's hand has ever gone up. I love you guys, okay. Who thinks it's bad? Raise your hands. All right, thank you. Who doesn't know or doesn't choose to answer? A few. My husband among them. Okay. He's just being cute. Okay. Okay, so I'm doing I'm taking this survey. And the point of it is to make the simple point that you already do have an opinion about valuing the future. I raised this question, what do we think about the future? Do we want to save it? Is it important to us? And you have all voted, most of you have voted on the side of taking some measure to preserve the future because for whatever reason you think it's important. I think this is very important. I think there's a core of moral belief, whether it's aesthetic, value, or whatever, within each one of us, and we need to build on that. We need to figure out where it came from and how it can be magnified. Thank you.
Ok, entonces llegamos a la hora de preguntas. Les vamos a pedir que aquellos que tampoco quieren hacer su pregunta, tenemos 2 personas en los pasillos con papelitos. Les pueden pedir un papelito y nosotros con todo gusto lo leeremos. Entonces, ¿alguna pregunta? You were so clear. There is no questions. Thank you.
Let's get beyond what I said.
Well, first, thank you. I think your work is exemplary. You have amazing insights. I think you're amazing. Secondly, where would you put human action if you were to lead us somewhere? As you say, our moral compass has been leading us in some directions that may cause the earth to be beyond repair. And I would ask you, would you put your faith in science? Would you choose maybe machine learning or astronomy or math? How would you go about tackling this issue?
Great question. What next? So I don't think that we do things for rational reasons, really. I think we do things out of feeling and caring. And I think what's missing thus far is a value for the future that is strong as my value for, say, our fellow people. You know, we feel outraged when somebody is killed. We can't imagine murdering somebody else because we value that person. We grew up that way. It's part of our genetic code. I would like to think that we can generate that kind of love and devotion for the future of Earth and the destiny of humanity. It will almost be a religious belief. It will be a shared cosmology. And it will be heretical to do anything that would try to damage that promise. We're not there yet, though.
I think this issue is closely related with philosophy. About the question that you raised, I have a question for you. Are you assuming objective moral values? I mean, do you believe that objective moral values actually exist?
No.
So how do you prefer, or how do you explain that you use the word good or bad? I mean, how do you found such terms?
Perfect question. You've gone right to the heart of it. So obviously, among us, we're going to differ here. I offer my view humbly for your consideration. I've been watching a lot of films on the internet about moral behavior in animals. And you can just see the seeds of human morality in monkeys, elephants, all kinds of higher level mammals. I think that a moral system is a way of making decisions. And each life form has a strategy for making those decisions. For better or for worse, our strategy is to be social, and therefore some of our decisions need to protect society. But at the same time, we have to look after our own bodies because our genes will not propagate unless we live long enough and raise children. So we have to be selfish in order to make that happen. So I think that the human moral code is a trade-off between those two impulses. And I think it's mostly built into us and then reinforced by our childhood and upbringing. I think that the basic existence of this code is inherent in us as humans, and I don't think we could change that. But I do think that aspects of it can change. And I'm very encouraged by the fact that our moral code has been enlarging in recent centuries. You know, 200 years ago, certain people were not considered to be fully human. Even today, in some places, women are not considered to be fully human. But these things are changing. If we could bring future generations into our tent and think about them as intimately and deeply as we think about our families, our cities, our countries today, that would solve our problem, and I don't think that's impossible. That was a long answer, I apologize.
Well, I got a question. Why are you so optimistic about a theme that maybe in your survey, you said that in 3,000 years, or how?
I said 1,000.
Okay.
Just far enough in the future
well,
that I can't blame anybody today.
Yeah, okay. Well, how we know that that's the certain future, that we know that the Earth had a lot of seasons, like ice age and that. So we are taking the fact that the dinosaurs died because of the Chicxulub, but why do we don't know that maybe they could die after if the Chicxulub didn't happen with an ice age? And we know that climate change is a normal thing in the Earth. So maybe we're not the cause, maybe we are only contributing to the climate change. Maybe we're not the reason or the origin of the climate change. So
This is true, but the essence of my question, which was a hypothetical question, I told you the fact that disaster happened and we were to blame. Now, I don't know that that's going to happen, but I wanted you to deal with those circumstances in trying to decide whether you thought that was a good outcome or a bad outcome.
but we can think if that's a good thing or a bad thing because we are not the cause of the climate change.
I don't want to get completely stuck on climate change. We did something bad in my example. Maybe it was radioactivity, maybe it was nuclear war, I don't know.
So you think that we could colonize another planet, maybe?
That's a very good question. I think it would be good if we did, because you can see the consequences of living for a long time on our planet will constrain our creativity. We have been living through a miracle for the last 2 centuries in which the number of people have grown and our ability to consume and exploit resources have grown. That can't continue. We've done great things during that time. Science has flourished. Science is living at the top of the environmental pyramid, right? We're all guilty as scientists for living on a system which is consuming resources at a great rate. So I think it would be nice if we could expand. I think growth is a wonderful engine of creativity. In order to voyage to the stars, the main thing we have to do is have longer lives. Maybe we should genetically engineer in that direction so that we can live longer. It's not that we're small, it's that we're short-lived.
Hi. Sandy is my mom, so you know. And I know, obviously, I've had a front row seat for your career for 47 years now. And I know at the beginning, when we listen to introductions of you, there's a lot of science at the beginning of your career, which is amazing and wonderful. But lately, talking to you and coming to your presentations, there's this shift from what does science mean to what does science mean for us. And what I can see is that, and you may disagree, but this seems to be something that as you've gotten older in your career is becoming more and more of a topic for you. And I'm considering we're addressing a bunch of people at the beginning of their careers. I'm kind of in the middle here. And I'm thinking it would be nice if we could all start thinking a lot younger at the beginning of a scientific career now, more the way you're thinking. What does this mean for us? Where are we going? And what does my science or my contribution mean for living sustainably and happily on this earth together? So I thought maybe you could talk about what caused that shift for you, when did it come about, and what advice would you give to us for how maybe we can get there earlier so that we can have an impact on our trajectory?
Thank you, Robin. You do me honor with that question. Yeah, so I think it all started from what my father used to say to me. I was lazy as a kid, believe me. And I had all these chores to do, and I never did them, and he was always flogging me and trying to get me to pull my weight. And his favorite expression was, make yourself useful, Sandra, make yourself useful. And so as time went on, and I was thinking about astronomical knowledge, it's been such a privilege to be supported by taxpayer dollars, and it's wonderful to go to a party and have everybody ask you about your work because people have a craving, a hunger for this. But I began to think, well, you know, we do spend millions, if not billions of dollars on this science. What good is it? You know, it doesn't make people healthier, it doesn't grow crops. What good is it? So I was motivated to try to generate this bigger story. And I'm completely convinced of the truth of it, that if we don't have a shared cosmology, we won't have any vision for the future. So I feel that though I personally, in my little lifetime, have done that tipping point thing that I'm talking about all of human race is doing, right? I went from some naive state in which it was just fun to do my thing and I enjoyed it. But now I'm taking my dad's words to heart and wondering really, what's the point? Where are we going? What's the big story? If we save the future, what are we saving? And why?
Beforehand, and this is not only question for you, but for all of the present here, about the human responsibility and this kind of thematic. Did Anione have questions if you want to change the human freedom for the human freedom for more how do you can say more stability.
¿Puedes hablar en español si quieres y le traducimos?
Bueno, está bien.
Oh, no, don't.
No, puedes seguir intentando. Más bien es como, si quieres, puedes decirlo también en español y le traducimos.
Bueno, la pregunta, el punto que quería llegar es que si algunos de ustedes han pensado en qué sería mejor, si mantener un estilo de vida como el que llevamos, pero con todo lo que implica, o intercambiar cosas como la individualidad y la libertad, la individualidad y la libertad a favor de una meta más común. Por ejemplo, un tipo de distopía que sería ahora sí que con un propósito.
I think maybe I understood. You're thinking about how we will weigh personal freedom versus restrictions and obligations to society going forward?
More or less.
Okay. I think that, again, we're in sort of a temporary stage where we've celebrated individual freedoms, the right to go out and strip mine some large, mountain in West Virginia, or make a gold mine that pollutes and so on. I mean, this is a whole economic philosophy in the United States, and I think it is here too. So I think we're coming to the end of that. And I think that all aspects of human life, including how many kids you're going to have. All of this is going to become more regulated as we try to make more optimum use of limited resources. You know, you can't sit anywhere on the plane, right? The plane is a finite resource. You've got your seat, you sit there, and you accept that in return for the ability to fly. That's what we're going to have to do if we want to fly.
Tenemos una pregunta por allá y después acá, ¿ok?
So, when you were mentioning the factors that determine whether a Earth is a probable planet on the universe, you mentioned a safe zone where the planet should orbit in a particular sun.
Mm-hmm.
And you left me thinking, you later talked about an idea that was to, if we wanted to preserve the Earth, we can move we can change the orbit of the Earth by moving it. So
Yep.
how, if you can answer it with more detail, because you left me thinking with that idea.
So if you want to move Earth farther away from the sun, you have to do two things. You have to give it more angular momentum, and you have to give it more energy. You have to help it climb out of the potential well. So energy and angular momentum are conserved. You have to get that from somewhere. So the goal would be to get it from a planet like Venus, which has more specific angular momentum. So the goal, the idea is to take an asteroid, not a huge one, which you would put into an elliptical orbit so that in the outer part of the orbit, it would come close to Earth. It doesn't hit Earth, it gets close. But there's a little bit of a gravitational collision and an exchange of energy and angular momentum there. And then in the inner part of its orbit, it's kissing Venus in the same way. And so it's possible to structure those encounters such that that little asteroid will take energy and angular momentum from Venus in its collision with Venus and deposit it with Earth later. And the net result is that Venus moves inward and Earth moves outward. People write papers about this, actually.
And do you really think human moral is growing exponentially, or at least in a constant way, so that we are not falling again as we did in the Middle Ages? Because we were going really well, right? From the ancient ages and the Roman Empire and Greece and all those great civilizations, and then the Middle Ages, right? But that was not a really great problem because there were not many people in the earth. Now we are millions more, and in the future we may be many millions more. Then if we fall again, is there a chance that we may rise and the earth comes to a good end as you wish that it makes?
Not sure I got the last bit.
Okay. Okay, my question is, do you really think we're able to save the earth?
I would say we're the ones to start to save the earth. Because if we don't start to save the earth, then it's downhill from here. We don't want that to happen. Yeah.
Okay, I have a question, here in a paper, and then you can ask your question, okay? You can read it? No.
No, go ahead.
USA, as a nation, is famous for its ideal of reaching a better future, but improving in an economic basis. I imagine this is because a lot of people believe that this is right. What it means, it is part of the culture. How do you think this could match with anything we, every human being, could do in order to help our human future?
So I think you're referring to the culture, the economic culture in the United States, which has been a growth-oriented culture. I think we inherited a lot of our views in the United States because we came to a continent which from the white person's point of view, was uninhabited. Of course, it wasn't. But there were vast reaches out there that could be exploited. And much of our culture was formed in an age when, if you didn't like where you lived, you could just move west and start over again. So there was always new land, always new resources that could be exploited. And we've generated an economy that's based on that kind of philosophy. I think you're asking me if I think that can continue? No, I don't think so. And I know that, somebody else who said this historically was Malthus. He was focused more on the number of people rather than the consumption of resources. I don't think it's so much people, it's what we consume. We laugh at Malthus now, but he was right. He was only ahead of his time. And now, this tipping point that we're at, this is when Malthus is going to come true. And we're going to see big changes, like it or not. That's my feeling.
Sandy, you mentioned this original institute about the future. Could you tell us more details about this? What is the mission, the goals? Which specialists do work in this institute?
So this institute it barely exists, right? So it's an infant. As far as the goal is concerned, it's different because it has this long time scale and because it has this ethical, moral component. We have something called the Center for Public Philosophy there. Here's my picture. My picture is that scientists and social scientists will continue to do their quantitative work. They will produce papers about resource use, policy statements, and so on, which are boring and incomprehensible to most people. So we need a way of translating the truth in those documents into stories. This is how we really learn. This is how your parents taught you. They told you stories. Into stories which touch our souls and hearts. And so there's a middle component there of artists and writers and even video gamers, because I think video games can teach us a whole lot. They're really computerized stories, right? And they will be disseminated to the public. I think if our institute could have a partnership with Hollywood, that would be absolutely perfect. Now, the goal of this is just to get the public thinking and talking. And that's the farthest that I can see right now. Because if we as a species don't adopt a general point, it's not going to be a small number of elite thinkers that make a change. No, the whole planet has to change direction. So this little institute with its 3 parts is an attempt to start that.
Sabemos que tienen millones de preguntas, pero se nos acaba el tiempo, entonces esta será la última pregunta. Nada más que no vi dónde quedó el micrófono. Allá atrás.
Buenas tardes.
Vaya primero, perdón.
Sí. Bueno, sé que no lo mencionó en la conferencia.
Más alto.
Sé que no lo mencionó en la conferencia, sin embargo, sé que hay un cambio, bueno, la Tierra está teniendo un cambio en el polo magnético, sí, en su polo magnético, entonces quería saber si eso podría afectar su órbita y de ser así, ¿cómo nos afectaría a los humanos? Gracias.
She knows that the magnetic pole is changing, so she wants to know if that can change the orbit of the Earth and how that can change to our way of life.
You've told me something I didn't know. The Earth's magnetic field is not constant. It does wander. Even more importantly, though, it can change polarity. It goes from north to south every few million years, I think. We have that record in the rocks. So no, the Earth's magnetic field has nothing to do with the orbit of the Earth, 2 separate things. The Earth's magnetic field is generated in its interior. It's separate from the orbital properties. An interesting question is, though, when the field reverses polarity, we lose our magnetosphere. We lose protection from the sun. It's one of the dangers that I didn't think of putting in my talk. And people wonder about that. Maybe there's a brief period of intense irradiation of when we're vulnerable, when the field is changing. So the field is really important. And knowing more about it would be a good thing. I'm going to stop there, and thank you all for being such great listeners and wonderful questions. Thank you so much.
Thank you. So now I invite Dr. Stern, Dr. Lee, Dr. Gonzalez to give you a little present, and thank you, Dr. Faber, for your amazing conference today.
Thank you very much for your amazing conference and unexpected. This is just, thank you, and this is a present from UNAM.
Wow.
Si nos ayudan a ponerse tantito para adelante. Un poquito para adelante, por favor.
Ahí, he wants us to come forward so that you can see it there.
¿Cómo se dice grabado?
It's great. Yep.
It's an engraving of a Mexican artist.
Is this a new thing?
Is
it new or is it old?
It's new.
It's new.
It's new.
Yeah, it's beautiful.
Not of this year, but it's new.
That's
A couple of years ago.
Hmm.
And I hope you like it.
I love it.
So this is a present from everybody.
I love it. It looks.
Gracias.
Bueno, gracias a todos.